Hi, my name is Lojunsen. Today I will be presenting my project, which is classification on the testing product image data for quality inspection by using deep learning. So this system is designed to identify the defect in testing product images through using the convolution neural network. So the dataset I found is from Kage. Uh, so we can see that the dataset is can be categorized to two category, which is non-defective, it's mean okay, and defective. So the dataset we can see it is well split to training set and test set. Let us go through to the code. So before we start, for sure we need to import the essential library that will be used to design the deep learning. So basically, the more of I using from TensorFlow Keras. Okay, so we start on part one, data preprocessing and augmentation. So at the first, I wrote a program to verify and check the total data set. So for the total overall data, defect and okay. So the next one is before we do any augmentation, we visualize the current data first for few of the current data for defect and also okay. So we can clearly see the difference. For defect, we can see some distortion on the product. For okay is pretty good. Okay. So the next one is about data augmentation. So from here, what what I do in here, the first one is rescaling the pixels to zero, the range 0 to 1. So that can be fit into the convolution neural network. So another thing is I apply the rotation range, width, height shape, zoom range, horizontal fleet, binary range. So for augment the data for better training to prevent overfitting issue. We then set up for the image data generator. So we supply this train data generator to the variable. So we also set the batch type as 64 to have speed up the training process. Since the we are training in Kage have large memory usage for us, so we can use it. Same goes to validation and generator. Okay, but the difference with training set is validate data generator. We are only rescaling the pixels and split the training data uh, for validate split to 20% from the training data. So also for test data, so you can see this is the command message from each of the training set and test set. After we set all the important data set, the train set, validation set, and test set, so we verified some few of the augmented images. Okay, from here you can see some of the image was rotated, some of already begin flip, and also zoom. So now let's us talk about the model architecture design. Okay, so for the part one, it's about convolution neural network setup. So we using the model sequential library from the sequential library, and in this convolution neural network, it consists two convolution layers, which is layer one and layer two. Okay, the layer one has 18 unit of the layer, and the second convolution layer consists of 16 unit. Each of the convolution network followed by the batch normalization layer and max pool 2D layer. for better generalization. After we flat the output to the dense layer with 64 units by using activation layer. So we to prevent overfitting, we add a dropout layer with 20%, and at the output layer, we combine all the neuron into dense layer, a single dense layer, with the activation sigma for binary classification. So after all the setup, we see the summary for the model. So we can see they have total of parameter with around 3.2 millions. This setup balance the efficiency and accuracy while keeping the model lightweight. So now let us continue to the second part of the architecture design. Okay, so let's start with callback setup. The first callback technique that we use is early stopping. So we implement early stopping to monitoring the validation loss. Uh, meanwhile, if the model epoch is not improving in eight continuous epoch, so the model will restore the best weight. Next callback technique is model checkpoint. We implement this to store the lowest validation loss model, uh, so to keep using in the future after the training process to ensure the best model that we use have efficiency and accuracy. After the callback technique, we declare a class weight. This is for compute the class weight dynamically since we have imbalanced dataset. This prevents the model being biased toward to the majority classes. Fine-tuning our model while training, we design a learning rate adjustment or scheduler. So this is as a dynamic type. Uh, So we monitor the validation loss. If they have three continuous spot does not improve, so we lower down with the factor 0.8 to the learning rate. So let the model can have better learning process. After all, we compile all the optimizer loss and metrics to the model. So the optimizer we use Adam, and the loss we use binary cross entropy. So the metric we measure the accuracy. So after the compile, we direct train or feed the train data. So validate data and class weight and all the callback techniques to the model. So this training has running 50 epoch with the callbacks process, so we can get the better, efficient, effective, and generalization models. So this is the previous process. So the next part is part three. We evaluate and visualize the model after the training process. So this is the program that I write to call out the best model that we save in our storage. As we can see, the prompts. Okay, we call out by using naming epoch and also the minimum validation loss. Okay, so after that, let's see on the training and validation curve for accuracy and loss. So in here we can see that uh, at the at the accuracy part, we can see the training is increasing almost steady, but the validation is quite different since maybe it has some overfitting, but we get the best one is at the 7 approach. So for loss, okay, For loss, when training is also in decreasing steady, so we get better generalization. But when in measure in validation set, so you can get the minimum one is at roughly 0.1 and equals 7, 6 or 7. So the next one is we want to measure for F1 score for validation set. So the first we convert the probability to binary label. Okay. Okay. After we get the value 0 or 1, so we score for we check for F1 score on the validation set. From this F1 score, we can understand that our model achieved on overall F1 score of 0.93, so which pattern precision and recall effectively. The accuracy is 94%, meaning it's correctly classified most sample. Okay, so for class 0, representing okay product non-defective. So the precision is 92% and recall is 98%, meaning it's really classified defective product as okay. For class 1, representing defective products, precision is 98%, but the recall dropped to 89%, meaning some defective items are missed. So overall, the model performed well by improving recall for defective product could further enhance defect detection. So the technique like data augmentation or tuning class will maybe need to readjust. Next, if we see on the confusion metric, comparing the true label and predict label, so you can see most of the classes are detect correctly. So you can see for non-defect, okay, we get most of the result uh, appear here. And also for defect, okay, but only like got 13 label for non-defect is detect wrongly as defect. Non-defect detect as defect. And also for 62 true defect, but we detect as non-defect. So next one is test result. At first, we do the same thing to measure the F1 score and also confusion metric to the test set. Okay, this is what we get. Okay, more probably the F1 score is read as pretty good. Okay, since have accuracy on 97%. Okay, so this is confusion metric for test set. Okay, you can see that most of the uh, classes are correctly detect. Okay, so the next one and also last part, I think I manually to generate a code. Okay, to write a code to predict the random image. So all of the function here is to randomly select an image from the storage. So from here, after converting, rescaling the image pixels to normalize the pixels, and then we predict the image. Okay, okay. So here we will get what we predict. Okay, so this is the main function to call main program to call the function. Okay, data predict random image, and then data directory is the folder for the test set. So here, this is one of the result that I try to run, and then the image is from actually from non-defect folder. Okay, it's been okay. So the class has been detected is also returned okay, also non-defected. So pretty class non-defective. Okay, so that's mean our program is well detect and it is effective and generalized on this application.